Hey everybody, here we are doing SIG number 9. I'm going to walk you through how to do these problems, but before I do that, I just want to explain again like why we did Riemann sums. The purpose of this was if we were given some sort of function, maybe like this, then like our question was like, how do we find this is before we knew how to integrate, right? How do we find the area under the curve of this function? Maybe let's go from here, from A to B, right? We wanted to figure out what that area was. And so one way we did that was we said, well, let's approximate the area using rectangles, right? So let's draw a bunch of rectangles, maybe like this. And everywhere one rectangle leaves off, you just draw another one like this, right? And then if we added all these rectangles together, right, if we added all these things up, we would have an approximation for the area. Right, so that's what the Riemann sum does. And then later what we talked about is like, well, what if we made these rectangles smaller, right? What if we made them really narrow? What if we just made them infinitesimally smaller, like really narrow? Then we'd actually get the exact area, which that's what turns out. The notation for adding, right? This is this symbol here. And basically what we do is we add like this, where the delta x is the base and the f of x sub n is basically the y coordinate of these points. Right? And so by multiplying those, you're doing height times base, or base times height. And what happens to this is remember, we're summing things, right? We're adding a bunch of things up. So basically this summation notation turns into this S-looking thing, right? So like, I can write that down here. That summation thing turns into this S-looking thing. And the f of x, and then delta x, instead of being like that triangle, we just use dx. And then, it's going from A to B like that. So like this summation notation eventually like turns into the integral. All right, so now that we've done that, let's look at how we actually do this problem. Okay, so I provided a graph just in case it's helpful for you to look at it, but at some point we want to be able to do it without a graph. So what we're going to do is we're going to go and just plot these points for now, just so we can see what this graph looks like. All right, so I'm plotting 0, 5, 1, 7, 7, 8, 8, 6, and 9. Oops. 8, 6, and 9, 7. And so when you're doing, sketching these points, they do not need to be exact. They just need to give you approximations. Like, it just needs to be close. It's just a visual aid. Right, so those are those. So what we're going to do here is we're going to use a left-hand Riemann sum to approximate the interval, which means we're going to be starting with the left-hand value here, right? So we're going to be starting over here, and we're going to draw a rectangle that goes all the way until it hits the next point that was given to us there. So we're going to draw that rectangle. And then we're going to start at this other point and draw a rectangle all the way over until it hits the next one. Right, and then we start at this one, we draw a rectangle that takes us to the next one, and that one takes us there. And then we notice how we don't end up using this, right? Because you don't need to write this, but we don't end up using this because we started at the left hand, and we're not going to end up using the right endpoint. right? So basically we have 4 rectangles here, right? All we need to do is find the area of those rectangles and add them together. Right, so our area is going to be, well, what's the area of R1? Well, base times height, right? So what's the base of this rectangle, right? Look down here. What's the base? That's 1 unit, right? It goes from 0 to 1, so that's 1 unit. So this is going to be 1 times, what's the height? Well, the height was determined by the left endpoint, so the height was the y coordinate here, which is this guy, which is 5. And then we'll do the next one. What's the base of this one? Well, this one goes from 1 to 7, right? How far is that? That's a distance of 6. So it's going to be 6 times, what's the height? Well, we'll use this one for height. We'll use the y coordinate when x is 1 for height, right? We use this piece right here. And so that's this 7. Right, and then we're going to add the third rectangle, which has a base of 1 and a height of this y coordinate there. That's how we found that one, which was 8. So that's going to be 1 times 8. And then we're going to add the last one, which is going to be a base of 1 and a height of 7. Right, and so now all we have to do is multiply these. So it's going to be 5 plus 42 plus 8 plus 7, which is 47 plus 15, which is going to be 62, and then units squared in this case. Since it's area, we're talking about square units. And so there you go, that's the answer. And I just wanted to show you real quick how we could use the table. Notice that the base is basically this, and if we're using the left endpoint, then we use this number, right? And then the next base would be from there to there, right? So it's like this is 1, this is 6, and then we would have used for this one, we would have used this height, right, because it's the left endpoint. And then the next one would have been a base of 1 again, but we would have used this height. And then the next one would have been another base of 1, because from 8 to 9 is 1, and we would have used this height, right? And so you'd basically take 1 times 5, 6 times 7, 1 times 8, and 1 times 6, which is what we did here. Right? So if you can see in the table, then you can save yourself some time by not graphing, but the graphing is not that hard, so I'd suggest just doing it anyway. And so, okay, so next one is we're going to use a right-hand Riemann sum to approximate it. Let's go ahead and graph these points again. Okay, those are those, and I like to go and draw these lines coming down so you can see where they go to. Again, it doesn't have to be perfect. And we're going to use a right-hand Riemann sum, which means we're going to be starting at the right endpoint, right? We're going to start over here, and we're going to go to the right until we get to the next number, which means we're going to go there, and then we're going to use this point to go over, make that rectangle there. We're going to use this one to go over until we get to the next one there, and then this one will take us the rest of the way to there. Right, and again we have 4 rectangles. I'm going to label them this way since we started on the right. And so our area is going to be approximated by and you know, I labeled them backwards, so let's go ahead and do these ones backwards. And like, let's find the area of this first rectangle. Again, it's going to be base times height, so it's going to be base times height, right? So that's going to be, the base here is 2, from 7 to 9 is 2, and the height here is the y coordinate when x is 9, which in this case is 7, right? And then we're going to add that to the base times the height, which here the base is 1, and the height is the y coordinate when x is 7, which is 6. And then we're going to do the next one, which is base times height, which is the, from 1 to 6 is 5 units. So 5 times the height is when using the x coordinate of 6, which is 8. And then the last one is a base of 1 times a height of 7. That was this one. And we would add all these together, right? So our area is going to be approximated by 14 plus 6 plus 40 plus 7, which is 20 plus 47, which is 67 units squared. And again, we are approximating the integral as well, right? So the approximation of the integral, which remember is the area under the curve, is about 67. Okay, last one, which is probably a little bit harder because you're given a function instead of the table. But again, I think the easiest way here is going to be to construct a graph and just graph some points and then go from there. So let's go and create this. We're going to be going from 2 to 4. So actually, let me just make this bigger because we don't need to be. I need to be stingy with space on this. And then the biggest thing here is we need to figure out how to divide this, right? With the tables up there, it was pretty obvious how to divide it, but this one we need to use 4 trapezoids, right? Which means I need to divide this space that's going to be given to me here, right? We're going from 2 to 4. I need to divide this into 4 equal pieces, right? So the way we're going to do this is what we're basically finding is our delta x is basically taking our interval and dividing by the number of rectangles or trapezoids that we're trying to find. So in this case, it's 1/2. So my interval should have should each be 1/2 unit in length, right? So in which case I start at 2, I'm going to count over half, which is going to put me at 2.5, right? So the next, one of these regions is going to be through there, and then I'm going to count over half again, right? 2.5 plus half is 3, so the next one's going to put me there, and then 3 plus 0.5 is going to put us at 3.5, which will put us there, and then 3.5 plus 0.5 is at 4, and so you can see we have 4 regions here, right? We have 1, 2, 3, 4 regions. Right, and so that's how this helped us, is it found the width of each region. Now basically we need to find out where's our y coordinate on each of these pieces, right? So basically what we're going to be doing is we're going to be just finding the y values at each of these x values. We're going to find the y values, right? So we're going to find f of 2. Which if you plug that into the equation, it's it's 2 squared, which is 4, divided by 2 is 2, -2 plus 2 plus 5. So this one gives us 5, right? Then we're going to find f of 2.5. Now I don't want to make a mistake on this. I'm going to go ahead and use the calculator, which you're allowed to do on this problem, and try to turn it on. All right. So we're going to do, let's put it up here. Let's do negative x squared divided by 2 plus x plus 5, right? And then we're going to go back to this screen and just do alpha trace y1 of 2.5 equals 4.375, and then we're going to do f of 3 which is 3.5. And we're going to do f of 3.5. Which is 2.375. And then lastly, we do need the last one on here too, which is f of 4, which in this case is 1. Right, so let's just go and plot these points, even though you don't need to. We're going to plot them. Or so 5, let's say 1, 2, 3, 4, 5. That one's here. 2.5 is 4.3 something, which is might be there. 3.5 might be there. 3.5, 2.3 something, gonna be there. And then 4, 1. Like that, right? And so basically what we're going to do is we're going to create trapezoids, right? Trapezoids, in this case it looks kind of like a straight line, which it's not, but we're going to create 4 trapezoids, right? And we're going to try to find the area of each trapezoid. So it's important to remember that the area of a trapezoid is height 1 plus height 2 times the base over 2. I like to remember it that way. It's a little bit easier. So what that's going to be is height 1 is right here for this. So for T1, so let's write this out. The area of this trapezoid is going to be T1 plus T2 plus T3 plus T4, right? So for T1, the height 1 is the function value at x equals 2, right? Height 1 is this. So height 1 is basically f of 2. Height 2 is basically f of 2.5. And then we're going to multiply that by the base over 2. So the base was 0.5 divided by 2. That's T1. And then trapezoid 2, height 1 is the function value at 2.5. And height 2 is the function value at 3. So this one's going to be f of 2.5 plus f of 3 times the base, which is 0.5 over 2. Right? And then trapezoid number 3 is going to be over here, right? It was going to be height 1 is there, is the function value at 3, and height 2 is the function value at 3.5. So it's going to be f of 3 plus f of 3.5 times the base over 2. And notice we're multiplying that same thing over and over again, right? So maybe we can create a pattern there. And then the last one's going to be f of 3.5 plus f of 4 times the base over 2. All right, so it looks really long, kind of because I wrote big too. But if you recognize the pattern, then we can make this a lot easier. So let's go ahead and write this out. Like, notice every single time we had to write this, right? So we can just like factor that out. Let's just write that over here. And then we'll write what's left, right? F of 2 plus f of 2.5. We actually calculated these already, right? F of 2 was 5. F of 2.5 was 4.375. Right? And then plus f of 2.5 again was 4.375. Are we doing this? Plus f of 3 was 3.5. And then we're going to add that to f of 3, which again was 3.5, plus f of 3.5, which was 2.375. And then we're going to add that to the f of 3.5 again, right? We're here. plus f of, oh sorry, I was writing the numbers down. So f of 3.5 is 2.375 plus f of 4, which was 1, right? And remember, all those yellow pieces are taken care of by multiplying out here, right, where this is a 2. And so since you have a calculator, you can just put this whole thing on your calculator if you want, but I also want you to notice that like all these inside numbers happen twice, right? Because they get used as h1, and then for the next trapezoid they get used as h2, or vice versa anyway. And then the only ones that don't get used twice are the first one and the last one, right? So like if you really wanted to, this is not something you have to do, but you could write, we have 2 of these 4.375s plus 2 of these 3.5s plus 2 of these 2.375s, and then just 1, 1 like that. So that's, you know, that would make it easier. So let's go ahead and do this. So we're going to do 0.5 divided by 2, parentheses, 5 plus 2 times 4.375 plus 2 times 3.5 plus 2 times 2.375 plus 1. And we're getting 6.625. Right, this is our approximation. Please read the instructions, or don't forget, on this one it also asks to find the exact area using integration. So this is the approximate, right? This is approximate. The exact area is just going to be what you learned hopefully in SIG number 6, which is the integral from a to b of f of x dx. So in this case it's going to be the integral from 2 to 4 of our function, which was negative x squared over 2 plus x plus 5. So let's just do this on the calculator. We're going to do math 8, no, not derivative, integral math 9, 2 to 4 of, we put this as y1, so I'm going to put it there, and we're going to get the exact area is 6.667. Right, so our estimate was decently close, but not quite. All right, I hope this is helpful. Sorry it's so long. I just was trying to explain the concepts instead of just the process.